So we've seen this problem before. The last time we solved this problem, I told you could solve it one of two ways, with either the disk method or the shell method. The last time we solved it with the shell method, so I will show you now how to solve it with the disk method. And you get the same answer either way, and it's about the same amount of work. I just wanted to demonstrate that to you. So the question here is, what is the volume of a solid of revolution generated with these three functions and rotated around the vertical line x equals some value a? We don't know what that is. So in order to evaluate this using the shell method, what you would do is we would find two functions that were expressed with the same variable that our axis of rotation was expressed in. So because our axis of rotation was expressed in terms of x, we have x equals some value a. If we were to use the shell method, we would find two functions, f of x and h of x, and that would allow us to use the shell method. If, on the other hand, we want to use the disk method, we have to do the opposite. We have to find two functions that are expressed in variables opposite this. So instead of being expressed in x, we want two functions expressed in y, such as f of y and g of y. And let's see if we can do that. To start off, we need to take these two expressions and write them in function notation. This is a very poorly drawn g, just know that that's supposed to be a g. Anyway, so x equals 0 rather, is the same thing as g of y equals 0. And this may be a little bit counterintuitive with your x changing to a y here, but if you think about it, if you were to say x equals y, then you could write g of y equals y, and that would make perfect sense. It just so happens that in this particular case, we have 0 y's. So we can still write it as g of y, there are just no y's to be found. And with the same logic, we can do turn this y equals 0 into h of x equals 0, just so everything's in function notation, and this is fine. And so now we have one function expressed in terms of y like we wanted. We want another function, and we want this function because this is the only other one that we can express in terms of y. And so to express this function in terms of y, we need to solve for x like we did up here. And so we start off by subtracting the y to the 1/2 over to get our x isolated, and then square both sides to get rid of the exponent. So we have x equals a to the 1/2 minus y to the 1/2 squared. And if you watch the other video and you recall, this is exactly parallel to that. This, in the other video, we had y equals a to the 1/2 minus x to the 1/2 squared. This time, the variables are just switched, and this makes perfect sense if you consider the original function we're given. So we can write this as, because it's equal to x, we can write this as f of y equals a to the 1/2 minus y to the 1/2, all that squared. Now we have two functions expressed in terms of y. We have f of y and g of y, and our axis of rotation is x. So because these two are the same and this is different, we can use the disk method. If all of them were the same, we would use the shell method. But because this one's different, we use the disk. And to start off, it starts off exactly the same, as we need to know what domain we're on, or range rather, because we're dealing in y's. So to do that, we need to set these two functions equal to each other and see where they cross. So if we do that, because g of y is 0, this is very easy to solve. You just square root both sides and then add y to the 1/2 over to get this, and then you square both sides to get y equals a. And in this shell method, it was x equals a. So again, it's very, very similar to what we did before so far. So now this is one bound for our integration. This is the upper bound of what we are interested in. The lower bound is given here with y equals 0. We just wrote it as h of x equals 0 because we wanted all of these functions in function notation just so we knew where we stood on that. But now then, we want to express it as y equals 0 again, so we can just state that. These are identical statements, so we can just say that, and now we have clearly two bounds of integration. We have a lower bound of integration at y equals 0 and an upper bound of integration at y equals a. Now here, we can set up a range that y is a member between 0 and a inclusive, where a is greater than 0. And I explained this in the other video that a cannot be equal to 0, because if you had the range 0, 0, then when you integrate that, that will be 0 regardless, because there is no depth to that, because integration is the infinite sum of rectangles inside of a between two curves, and there are no rectangles there. That rectangle has a width of 0, and so your volume of your solid revolution would be 0. There is no solid in that case, if that made any sense. And we don't want it to be less than 0, because then this would be backwards. So because we wrote it as 0, a, we want a to be positive. We could have written it as a, 0, but I don't want to have to deal with negative numbers, and so I just made it positive. So that's how that happened. Now then, like any other problem, we need to find some number to test this with, because I refuse to look at a graph. And so, showing you things on the side. And so to do that, because we can't just subtract some value from a, because we don't know what a is, we need to express our value c in terms of a. And the only way that, the best way at least, that we can do that is to find the average of these two numbers, because that will work regardless of what a is, and it'll work every time, and it will work regardless of what this number is. It just happens to be 0, so it turns out relatively nice for us. So to find the average of these, we just add them. 0 plus a is just a, and then divide by 2. So a over 2 is guaranteed to be in this interval. Okay, picking up where we left off. With c equals a over 2, we need to plug this in to f of y and into g of y. And if we plug it into f of y, this math is exactly identical to what we did in the shell method. We have a to the 1/2 minus, this was y to the 1/2 squared, but we're plugging in c, so it's a to the 1/2 minus a over 2 to the 1/2 squared, which is, we can distribute this square root right here, say a to the 1/2 minus a to the 1/2 over square root 2, find a common denominator just by multiplying square root 2 over, and this is all still inside this binomial being squared, so not breaking any rules here. So we have square root of 2, a to the 1/2 minus a to the 1/2 over square root 2. What we can do here is we can factor out an a to the 1/2 like we did last time, get a to the 1/2 times the coefficients of square root of 2 minus 1 over square root of 2, and all that squared. So now we can go ahead and square this. Square root of a squared is a, this squared is this squared, and then square root of 2 squared is just 2. And so last time we looked at how, because 2 is greater than 1, that this would always be positive, but it would be positive regardless because it's being squared. So this could very well be greater than 1, less than 1, pardon, to get a negative value in here. But because it's being squared, this expression will always be positive, because inside something being squared is always positive. This a we defined as positive, and 2 is positive by definition. And so f of c cannot help but be a positive number, and that's all we really need to know, because like last time, our g of c is just equal to 0, and any positive number is greater than 0. So we can say that f of c is greater than g of c, like up here. I actually made a mistake on the bottom of the page, which is why I have a supplementary page I'm going to be introducing in a moment, so be prepared for that. So f of c is greater than g of c, and we can say, because c is on that interval, that f of x is greater than g of x for that interval of 0 is less than y is less than a. And so what I didn't do last time was I forgot this step with the axis of rotation. And what we need to do here is, unlike the shell method, we have to take this into account with the disk method. And we have to figure out where our axis of rotation falls in this inequality. And so here, if I go ahead and put this down, when I say axis of rotation here, I'm really meaning this value that we're setting a line equal to. So in this case it'd be a. It's x equals a, so axis of rotation is just a for this purpose. So what I'm trying to prove is that a is greater than or equal to f of y. And how do I prove that? Well, we prove it with algebra, with math. Who'd have thunk it? So you have a is greater than f of y, which means a is greater than or equal to a to the 1/2 minus y to the 1/2 squared. So just square root both sides, get a to the 1/2 is greater than or equal to a to the 1/2 minus y to the 1/2. Subtract a to the 1/2 from both sides. So you have 0 is greater than or equal to negative y to the 1/2. And I'm just going to flip that over so that I have my variable on my left side because, you know, that's how I like it. And so I multiply by -1. By multiplying by -1, this sign flips. So I have positive y to the 1/2 is greater than or equal to 0. And then I square both sides to get y is greater than or equal to 0. Now, if we look at our range here, that's true. Y is never anything less than 0. So this proves this inequality here, their axis of rotation, is greater than f of y for any value y on this interval. And so it proves this. And so with that, we can now do something unique to the disk method. In the disk method, you have to define two more functions. You have to define this capital R of y and this lowercase r of y. And the way you do that is you set up this inequality on your interval, and your axis of rotation is on one end and is greater than or equal to, or less than or equal to was on this end. One function is greater than another function. And so your capital R is the far function. So if we were to look at this on the graph, this g of y would be our outside function, but this is just expressing that numerically. So here we can say capital R of y is g of y minus this AOR value. So this is just, again, minus a when I'm saying AOR here. And our lowercase r of y is just f of y minus a. So capital R simplifies to negative a, and lowercase r simplifies to this craziness. And we can work with this with the disk method formula. So using what we just found with this capital R of y being equal to negative a, and this lowercase r of y being equal to our a to the 1/2 minus y to the 1/2 squared minus a, then we can put that into the formula for the disk method, which is v equals pi, not 2 pi. In the shell method is 2 pi, in the disk method is only 1 pi, times the integral from 0 to a, this is our interval here, times r of y squared, capital R of y squared, which is going to be our negative a, minus lowercase r of y squared, which is this business, times dy. So what we're going to do is we're going to substitute those in. So negative a for r and this craziness for lowercase r. That's all that happened here. No math was done. And so in this step, negative a squared is positive a squared because it's negative 1 times a. Negative 1 squared is positive 1. You know how algebra works. Here, I'm going to FOIL out this inside binomial here. So I have a to the 1/2 squared is just a, and then we multiply and double. So negative y to the 1/2 times a to the 1/2 times 2 is negative 2 a to the 1/2 y to the 1/2. And then negative y to the 1/2 squared is just positive y. And then we still have this a that was hanging out over here. That's what happened here. And if you look, we have a positive a here and a negative a here, and they're both inside this square. And so that will cancel out. So that will be our next step, would just be to cancel those out, make it look nice. And now we're going to square this binomial. So we're going to square it, and the a squared stays minus negative 2 a to the 1/2 y to the 1/2 squared is positive 4 ay. Positive 4 ay. Here we're going to multiply and double. So we're adding exponents. Y to the 1/2 times y is y to the 3/2 times a to the 1/2 times negative 2 times 2. So it's going to be negative 4 a to the 1/2 y to the 3/2. Boom. And then just positive y squared is just positive y squared. That's all you need. And then dy, of course. And so from here, what I'm going to do, because I want this y, this is my highest power in this equation, I want this to be in the front and I want it to be positive. But the problem is that there's this negative 1 that's being distributed to everything inside here. That's going to make this negative. So instead of distributing it, I'm just going to factor it out. I'm going to factor out a negative 1 into the front. So I have negative pi times my integral. And so this is going to make, none of this is going to be distributed, but this a squared is going to become negative here. So it's just going to be y squared minus 4a to the 1/2 y to the 3/2 plus 4ay minus a squared, like that. And this is just factored out that -1. And from here, this is as good as we can get it. We can't really do anything more to this. And so we're going to go ahead and integrate. And to integrate, we have y squared, which is y cubed over 3. Over here, we have y is y to the 3/2. And again, this a is just coefficient. This you don't need to worry about doing anything with this a in terms of integration. So y to the 3/2, 2 is going to land on top. So 4 times 2 is 8. And then we increase the power by 1. So 3/2 becomes 5/2. And then we divide by the numerator of that by 5. So it's become 4 times 2 is 8. A to the 1/2 y to the 5/2 over 5. And then over here, 4ay, well, y integrated is just y squared over 2. And there's a 4 right here, so I just went ahead and canceled the denominator away. So I have 2ay squared. And then finally we have this negative a squared. But again, this is just a number. This isn't a variable. So this becomes negative a squared y. And then again, we evaluate it at 0 and at a. Now from here, I'm going to factor out a 15 in the denominator because I want this inside to be nice and easy to plug numbers into. So I'm going to factor out this 15. So negative pi over 15. This one had a 3. I need to give it a 5. So it's 5y cubed. This one has a 5. It needs a 3. So it's going to be negative 8 times 3 is 24. A squared y to the 5/2. And then plus, this has neither. So this needs times 5 times 3 is times 15. Times 2 is times 30. So it's plus 30 ay squared. And then this also has neither. So it's going to be times 5 times 3, which is just an entire 15. A squared y evaluated at 0 and a. My cat is making noises in the background. So from here, I'm going to factor out a y because that is the highest power I have, and it's always nice to have a y out front just so it cancels away very easily. So I'm just going to decrement all of these exponents by 1. Nothing crazy, nothing out of the ordinary. So here, now that it's in its best form, in my opinion, we're going to start plugging in numbers. And like I said, this 0 is going to go in there, and that entire term is going to cancel. So you just plug in the a. So it's going to be negative pi over 15 times a times 5a squared minus 24 a to the 1/2 a to the 3/2 plus 30a times a minus 15a squared. So the first thing I'm going to do is I'm going to combine like terms with 5a squared and negative 15a squared to get negative 10 a squared. And then if I multiply these out, this a to the 1/2 and a to the 3/2, well, that makes a squared because 1/2 plus 3/2 is 4/2 is 2. And you add exponents when you multiply. So this becomes negative 24a squared, and a make a squared, so plus 30a squared here. And so, if I combine all of my like terms here, then I have a negative 10a squared, a negative 24a squared, so if you add those, that's a negative 34a squared plus positive 30a squared. So that's going to leave me with a negative 4a squared inside these parentheses. So if I just go ahead and turn this over, beep. So you have, I can't find my paper. So if you have negative 4a squared inside there, well, this negative here and this negative here are going to cancel. You're going to get positive 4a cubed over 15. Positive 4a cubed pi over 15. Excuse me. And that, if we compare it to what we got via the shell method, is exactly the same. So that proves we're right. Good for us.